Welcome to my project bazaar. Let me discuss about the project Harmonic Analysis for Hyperspectral Image Classification integrated with PSO optimized SVM. Let us discuss about the abstract of the project. Hyperspectral images show similar statistical properties to natural grayscale or color photographic images. However, the classification of hyperspectral images is more challenging because of the very high dimensionality of the pixels and the small number of labeled examples typically available for learning. These peculiarities lead to particular signal processing problems, mainly characterized by indetermination and complex manifolds. There are several algorithms has been proposed to classify the hyperspectral image. In our project, a new novel method has been introduced, that is harmonic analysis based classification, such as HA, PSO and SVM approach. This new approach accurately classifies the cluster band with respect to their amplitude and phase. Harmonic analysis is introduced to extract the feature from hyperspectral image. Amplitude and phase features has been obtained by derived HA. Then select best feature among extracted feature by particle swarm optimization. Finally, classify the respective band with the related cluster, which is performed with the help of support vector machine, that is SVM. This classifier accurately classifies the band to respective cluster form. In prior work, instead of HA used MNF, PCA and ICA could extract features, and also for combination of PSO SVM could use CVSVM and GASVM. HA is first proposed to transform the pixels from spectral domain into frequency domain expressed by amplitude and phase residual, yielding more functional and discriminative features for classification purpose. The reconstructed image is adapted with PSO to optimize the penalty parameter C and the kernel parameter for SVM. Finally, the extracted features are classified with the optimized model. The main novelty and contributions of our work consist of twofold. By acting HA on a single pixel, a smooth curve in frequency domain represented by amplitude, phase and remainder can be obtained, which is considered to be more functional and discriminative for classification. Different from the traditional feature extraction technique, HA can better capture the functional relationship between spectral bands, taking into account the adjacent bands to extract the frequency features. If we discuss about the flow diagram for our process, here we read the input image from the dataset folder. Here we need to read the hyperspectral image. Check whether our input image is having more than 3 band images. If not, then we need to read the more than 3 band images, because hyperspectral images having more than 3 bands. And in the pre-processing step, we need to pre-process every band with Wiener filter algorithm. Next, in the harmonic analysis, we need to extract the harmonic features for every band. HA based feature extraction. HA is designed to express the time series using overlap sine and cosine waves, that is harmonics, in which a signal in time domain can be transformed into the frequency domain, represented by multiple overlap sine and cosine waves with different frequencies. Generally, any periodic waves can be expanded into Fourier forms. HA technique to hyperspectral image feature extraction. Although the traditional Fourier analysis, which is a two-dimensional transformation, can be used to transform hyperspectral image into a range of frequency images associated to each band in frequency domain. The reflected frequency changes of every pixel are based on specific band. Next, here we calculated the amplitude and phase values. These amplitude and phase values are passed to the PSO algorithm for getting the optimized values. In the PSO optimization, PSO shares many similarities with the evolutionary computation techniques such as genetic algorithm. The system initialized with a population of random solution and searches for optima by updating generation. However, unlike GA, PSO has no evaluation operators such as crossover and mutation. In PSO, the potential solutions called particles fly through the problem space by following the current optimum particles. In PSO algorithm contains a swarm of particles in which each particle indicates a potential solution. Particles fly through a multidimensional search space in which the position of each particle is adjusted according to its own experience and the experience of its neighbors. PSO system combines local search methods through self-experience with global search methods through neighboring experience, attempting to balance exploitation and exploration. The concept of witness is employed and candidate solutions to the problem are termed particles, each of which adjusts its flying based on the flying experiences of both itself and its companion. Particle I keeps track of its coordinates in the solution space, which are associated with the best solution and has achieved so far by the particle. This value called local best L best. Another best value that is tracked by the PSO is the best value obtained so far by any particle in its neighborhood of the particle. This value is called the global best, that is G best. Basic concept of PSO lies in accelerating each particle toward its local best and global best solution. Next, these optimized values are transformed to the SVM classifier. Support vector machines are the supervised learning algorithm which analyze data and recognize patterns used for classification and regression analysis. SVM maps input vectors to a higher dimensional vector space where an optimal hyperplane is constructed. Among the many hyperplanes available, there is only one hyperplane that maximizes the distance between itself and the nearest data vectors of each category. This hyperplane which maximizes the margin is called the optimal separating hyperplane, and the margin is defined as the sum of distances of the hyperplane and to the closest training vectors of each category. Classification by n-class SVM. The classes from the first clustering group are being assigned to the first left substring, while the classes of the second clustering group are being assigned to the right second substring. The process continues recursively until there is only one class per group, which defines the leaf and the decision tree. Next, we obtain the result for the harmonic analysis based PSO and SVM classifier. Let me discuss about the running procedure for our process. Select the hyperspec.m file in the current folder, right click that file and run for executing this process. This is the main window for the harmonic analysis for hyperspectral image. By pressing the read image button, we can browse the hyperspectral image in the dataset folder. Select the hyperspectral image. I display the hyperspectral image in the axis 1 plot. By moving the slider location, we can view the next band for the hyperspectral image, and by pressing the pre-processing button we can perform the Wiener filter operation. And here I display the pre-processing result for the hyperspectral image. Here also, by varying the slider band, we can see the bands for the hyperspectral image. Totally we are having a 224 band of the hyperspectral image. Next, by pressing the next button, we can move for the feature extraction window, and this is the feature extraction window for the our process. And by pressing the harmonic analysis, we can extract the harmonic features for the every band of our hyperspectral image. So this process will be executed for 224 band, so it will take some time for executing this process. We extracted the harmonic features. This is the feature values for the harmonic, that is amplitude and phases. Now by pressing the PSO button, we can perform the particle swarm optimization algorithm. This will also take some time because we need to extract the PSO features for every bands. Now we extracted the PSO features. Next, this is the test features by extracting the feature values using PSO. Now we perform the SVM classifier operation. By pressing the SVM button, we can perform the SVM support, that is support vector mission. So finally we extract the SVM classifier with every band, and this is the tree clusters band, and this is the paint metal sheets, this is the bitumen cluster band, this is the self-blocking bricks and shadows band. So this is the graphical representation for the trees, and this is the graphical representation for painted metal sheets. This is the bitumen for graphical representation between pixels and band indexes. This is graphical representation values for between band indexes for blocking bricks, and this is the shadows graphical representation. Finally, we got the segmented image with specified regions. Finally, we analyze the accuracy by pressing the analysis button. Here we got the accuracy for HASVM. We obtain 80% accuracy. Finally, developed a novel HA-based feature extraction method exploited a PSO-optimized SVM classification scheme. The proposed method leads to improved performance, and the PSO-optimized SVM presents a good trade-off between accuracy and computational time. Thank you.